Have you ever seen quantum phenomena in the macroscopic world? What would superposition, wave function collapse, and the uncertainty principle from the microscopic world look like when they appear in real human life? Before we witness a miracle, let's first do a quick review of superposition in microscopic particles. In the microscopic world, material particles such as photons, electrons, quarks, and gluons can exist in a mysterious state of superposition. If you ask a free electron, which exact position in space it occupies at a given moment, the only possible answer is that the question itself is meaningless. If we define the state of an electron being at a specific position in space as one of its position eigenstates, then the electron is actually in a superposition of all position eigenstates. That is to say, the electron simultaneously, in a virtual sense of possibility, occupies all possible positions in space. If no measurement is made, the electron will never actually appear near any one position. If we compare the electron's position state to a pot of food, it's simply a mixed stew. Not only can the position of a microscopic particle be in a superposition, its momentum, energy, spin direction, and so on can also be in superposition. For example, at every moment, an electron simultaneously has momentum values of every possible magnitude and direction. The momentum superposition is also a mixed stew. In our macroscopic world, you see that every object has a definite position. Your phone, car keys, and coffee cup are at every moment actually placed somewhere. To see something in a superposition state, in the three-dimensional space of the real world is practically impossible. But now the moment to witness a miracle has arrived. Imagine you are a taxi driver. In the small town where you live, every resident except you has a number from 1 to 100, a total of 100 people. On Friday night, you decide to go out to pick up passengers at 10 a.m. the next day. If we label the event of you picking up your first passenger after 10 a.m. tomorrow morning as event A, then on Friday night, since event A has not yet occurred, we cannot determine which passenger numbered 1 to 100 will be picked up in event A. That is to say, we cannot determine which number between 1 and 100 event A will fall on. But after all numbers are possible. So we consider that on Friday night, event A is in a superposition of these 100 numbers. Just like an electron can simultaneously, in a virtual sense, occupy 100 different spatial positions. When we say event A is in a superposition, it is absolutely not a metaphor or an analogy. Because when an electron is in a superposition of all spatial positions, it does not truly exist at all spatial positions at the same time. It only exhibits a detectable possibility or probability at each spatial position. That is to say, if you use an instrument to detect the electron's position through strong interaction, and repeat this countless times, the final calculated probability of the electron being detected at each spatial position is exactly the probability of the electron's appearance, manifested at each spatial position. The electron's possibilities or probabilities exist simultaneously at all spatial positions, but it cannot simultaneously and actually appear at all positions in space. By comparison, we can find that, before event A occurs, it likewise does not truly occur on any one numbered passenger, yet it can indeed occur in the future on every numbered passenger. In addition, because each passenger has different living habits, some call taxis more frequently, some prefer buses, some like going out, and some stay home sick. So for each numbered passenger, the probability of event A occurring is also different. The only difference is that, we can only say that when an electron is subjected to strong interaction with a measuring instrument, it will actually appear within a small region near a precise position, whereas event A in the macroscopic world can fully and truly occur on a specific numbered passenger. Therefore, before event A happens, it is completely a real-life version of a superposition event. In fact, just now we already talked about wave function collapse. In quantum mechanics, a particle's state is described by a complex-valued function, called the wave function. We say that when a particle is not being measured or external disturbance is very weak, it will be in a superposition state. At this time, the particle behaves more like a wave. The wave function can be used to describe a particle in a superposition state. But when a particle is measured by an instrument, or strongly interacts with another particle, the wave function can no longer describe what is happening to the particle. At this time, the particle will randomly collapse from a superposition state into a specific eigenstate. More precisely, it collapses into several mutually adjacent eigenstates. This leads to a measurement yielding a relatively precise value. For example, by measuring an electron's position, people can find that the electron appears within a very small region of space. Having understood wave function collapse, we return once again to the macroscopic world to look for wave function collapse events. At 10 a.m. on Saturday, you pick up your first passenger. At the moment the passenger gets into the car, event A finally collapses from a superposition state into a concrete eigenstate. Just like in the microscopic world described by quantum mechanics, the fact that you pick up this numbered passenger is random. You might say that wave function collapse in quantum mechanics is truly random, but which passenger will become the first one to get into the car seems random, yet it is actually pseudo-random. As long as the information is sufficiently complete, before event A occurs, it is possible to completely determine who will become the first passenger. This argument seems correct, but do not forget that each of the 100 passengers has conscious choices that can change the final outcome. If we could prove that humans do not have free will, then event A could be considered pseudo-random. But the key question is whether humans actually have free will that is not influenced by external factors, and can independently make decisions. This has always been a mystery in the scientific community. Therefore, we can consider that, after event A truly occurs, a wave function collapse-like event does indeed appear in the macroscopic world. Before continuing to look for macroscopic manifestations of the uncertainty principle, let's first review this fundamental principle in quantum mechanics. When we try to use concepts from classical physics such as velocity, position or energy, time, to describe particles in the microscopic world, we are constrained by Heisenberg's uncertainty principle. The uncertainty principle states that the uncertainty in a particle's position multiplied by the uncertainty in its momentum cannot be smaller than a very small constant. This constant is half of the reduced Planck constant. In measurement, the more precise a particle's position is, the more imprecise its momentum becomes, and vice versa. Now let's return to event A. Soon after dropping off the first passenger, you will pick up a second one, then a third. Let's consider this question from the perspective of time. If you want to know how many passengers in total have gotten into your car, then you must observe over a long period of time. That is to say, the greater the uncertainty along the time axis inside your car. In other words, the larger the observation time window, the closer the number of passengers who got into your car will be to the total number of passengers you picked up all day on Saturday. And the more precise the observed passenger count will be. On the other hand, the smaller the uncertainty along the time axis inside your car, the smaller the observation time window, the more the number of passengers in the car will deviate from your total passenger count for the whole day, and the more imprecise the observed passenger number will be. And this is the real-life version of the uncertainty principle. You might ask, why do we simulate the uncertainty principle in this way? Next, look at this comparison and you'll know the answer. Special relativity shows that time and space are equivalent to each other. They are tightly linked together by the conversion factor of the speed of light. Therefore, in macroscopic four-dimensional spacetime, we can treat the time axis as a dimension equivalent to space. Then the time window for observing the number of passengers in the car corresponds to, in the microscopic world, the uncertainty in a particle's spatial position. The number of passengers in the car corresponds to the particle's momentum. A small observation time window inside the car corresponds to a small uncertainty in the particle's position. Then a large uncertainty in the number of passengers getting into the car corresponds to a large uncertainty in the particle's momentum. In fact, such examples are everywhere in life. Before cards are dealt at a card table, the card you are about to draw is in a superposition state. 3 days in the future, when a real storm arrives, the superposition state of the weather will collapse into a definite state. The longer the time you spend, the sharper the knife you grind will become. What other quantum phenomena in the macroscopic world can you discover? Share them in the comments section. I hope that after watching this episode, your philosophical understanding and qualitative grasp of quantum mechanics can rise to a whole new level. See you next time, bye bye.